Hi everyone, this is Nari and welcome to my video. Development in screening display techniques has been a rising phenomenon. This is an iPhone 12 and it is made of an OLED screen. Comparing to a traditional LED screen, it has advantages including high refreshing rate and curved screen. Since 1987, OLED has become a type of digital display technique that is highly advanced with immense potential. It showed us a potential future just like those seen in sci-fi movies. But how can OLED make the fantasy come true? OLED stands for Organic Electroluminescent Diode. If we look at a screen closer, you can see the picture is actually formed by many tiny pixels. Each pixel has three colors, red, blue, and green, which formed all the colors we can see. A traditional LED screen has 7 layers. From bottom up, the layers are blacklight area, vertical polarizer, anode, liquid crystal layer, cathode, horizontal polarizer, and color filter. The backlight area only projects white light. We can treat the liquid crystal and polarizer as shutters. Electricity will go from the anode through the liquid crystal layer and reach the cathode, forming a circuit which drives the liquid layer to have certain orientation, and hereby control the amount of light that goes through. For an OLED screen, in contrast, it is made of organic material that lights up as we add voltages. The layers between two electrodes can be characterized by their functions as electronic transport layer, emission layer, and Hall transport layer. The color of the screen is controlled by the amount of electricity that goes through each pixel. So we can turn each individual pixel on and off while no backlight layer is needed. An electron hole is the lack of electron at a position where one could exist in an atom or atomic lattice. The electron holes overcome interface barrier and enters the HOMO of the Hall transport layer through anode, while the electrons enter the LUMO of the electronic transport layer through cathode. Therefore, the electrons will travel in between the organic layers and enters the emission layer. They combine in emission layer and become excitons. The unstable excitons return to its ground state by emitting light, and this is the process of electroluminescent. Let's take a closer look. In 1983, Tao and al. Published the first example of a low-voltage-driven luminance device. The bottom layer is an indium tin oxide, ITO, coated with glass. And on top of that is the first organic layer made of aromatic diamine. The second organic layer is made of 8-hydroxyquinoline aluminum, AlQ3. The top electrode is an alloy or mixture of magnesium and silver with an atomic ratio of 10:1. Organic electroluminescent material has been discovered for a long time already, but this is the first applicable example because AlQ3 enables the light to emit at low voltage as low as 2.5 volt. Why does AlQ3 have this property? The optical properties of AlQ3 in relation to its crystal structure was studied in this paper. They generated and analyzed the crystal structures of 3 AlQ3 crystals using X-ray powder diffraction analysis of 3 phases of AlQ3: alpha phase, beta phase, and gamma phase. Here is a crystal packing of AlQ3 alpha phase. Crystals of alpha AlQ3 are triclinic, with the space group of P1, and parameters are shown here. Characteristic diffraction peaks of alpha peaks are found in the structure determination of AlQ3 thin films, telling us that alpha structures are preferentially formed in the thin film. Another important layer in OLED is ITO, which stands for indium tin oxide. Indium tin oxide, ITO, is a ternary composition of indium, tin, and oxygen in varying proportions. Depending on oxygen content, it can either be described as a ceramic or alloy. Here is a hexagonal unit cell of ITO. The structure of ITO is determined by neuron power diffraction. ITO is rhombohedral space group R3 in a hexagonal basis. The detailed parameters are shown here. ITO has a high work function, which promotes injection of holes into the HOMO level of the organic layer. ITO was selected as OLED material for its electrical conductivity, optical transparency, and its low resistivity. Performance of the emission layer of OLED was determined by its ability to emit light under small voltages. Discussions about the effect of different molecular packing on the optical properties of AlQ3 concentrations are carried out. Generally, the organic molecules are electrically conductive as a result of delocalization of pi electrons caused by conjugation over part or all of the molecule. Researchers concluded that the optical properties in AlQ3 thin films are strictly related to their amorphous nature. Broad distribution of molecular packings enables favorable pi-pi overlaps between facing ligands to occur, which contributes to its optical properties. In 1992, scientists found that changing the glass where ITO was coated on into plastic would enable the display surface to curve. This is how OLEDs are able to be curved. In this iPhone, for example, the OLED was curved 180 degrees in order to save spaces at the bottom area of the phone, making it thinner at appearance. More applications of OLED include indoor lighting and advertising panels, where the fact that it can be curved can allow surprising and fashion display effects. Organic chemists are still devoted to research in the OLED materials, optimize its properties like lifespan and quantum efficiency. Engineers are also dedicated in advancing its sealing processes and outdoor performance. OLED showed us a promising future, similar to science fiction films, and it won't become reality without the effort of organic chemists. Our world is becoming an increasingly fascinating and interesting place, and changes are happening now, just with the effort of our generation.